Okay, thanks. Hello, everybody. My name is Shilati. I'm a first-year PhD student in Professor Ed Colgate's lab at Northwestern. And today I'll be talking a little bit about the work we've been doing to create a unified set of metrics for benchmarking robot fingers. So this project is a part of the HAND ERC, which was established in November of 2024 with the goal of revolutionizing the ability to augment human labor through the use of robot dexterity. So by the end of our second year, we want to have completed a robot hand system. And so as we've started this journey of creating this robot hand system, we've looked back on hands of the past that have been created. So some popular hands are the Shadow Dexterous hand, the Robonaut 2 hand, the Utah MIT hand, and the Stanford JPL hand. And as we read about these hands and actually went and saw some of them in person, we noticed that they all use different technologies to try to accomplish the same task. And we wanted a way to compare the different technologies that are used. So we started looking at metrics and benchmarks for robot manipulation, dexterous robot manipulation, and we found quite a few. Some examples are the YCB object set and the associated metrics, the different grasp taxonomies that people will try to match their robot hands grasps to, and then also the performance metrics and test methods from NIST. And so as we looked at these metrics, we kind of saw that these metrics overlook a lot of the individual components and interactions between the individual components where the issues in robot dexterity will actually arise. So we noticed as we looked at these hands that these issues often arise in the strong interactions between the fingers themselves, remotizers, which are typically tendons in these dexterous hands, and then the actuators. And some of these issues are kinematic coupling of degrees of freedom of the finger. We also have non-backdrivability of the finger, and then friction and elasticity introduced through remotizing the actuators, typically to the wrist. So we have our problem. The metrics that we currently have are, they look at these hands as like the whole system, looking at the ability to perform dexterous tasks and the strength of the hand as a whole. So in this project, we have two objectives. Our first objective is to create a unified set of metrics for benchmarking robot fingers. And then our second objective is to design and build test beds for evaluating these metrics. So starting with our first objective, we wanted to take a model-based approach to evaluating these robot fingers. So this is a very basic model. We have bones, joints, and tendons in our finger, and then we have actuators which provide energy to the system. That energy is mapped from the actuators through our motor radii, through our tendon routing mappings, and then through our manipulator Jacobian to our task space, which is what we actually want to control with this finger. So this model right here doesn't account for the mass and friction and elasticity of the finger. So we kind of expanded this model a little bit to include those mechanical effects of the finger. And we also reorganized this model using some of our principles of system theory. So on the left side, we have our efforts of the finger, which are our forces and our torques. And then on the right side, we have flows, which are velocities and angular velocities of the finger. And in the middle, we have our mechanical responsiveness of the finger, which maps between our efforts and flows. And so this model of the finger kind of gives us a nice way to categorize our metrics. And it also allows us to ensure that we're evaluating all of the aspects of the finger that we find important. So our categories are efforts, flows, mechanical responsiveness, and then we also added a durability category since these manipulators are expected to interact with their uncertain environments. And so from that categorization, in that finger model, we kind of derived a bunch of different metrics that give us insight into where some issues in robot dexterity are coming from. And then using these metrics, we also identified which test beds we will need to evaluate the metrics. So this matrix of metrics is organized in columns by the finger metric categories and in rows by the test beds. And then this brings us to our second objective, which is creating test beds for evaluating these metrics. So right now we're focused on creating our main finger test bed, which will allow us to evaluate the finger as a whole. This is kind of a rendering of the finger test bed. It has actuators that drive the finger, and then tendons going from the actuators to the finger, which are routed by our carpal tunnel, which route to the finger mount where the finger is mounted. And then we'll be able to place different test modules around the finger to evaluate our metrics. And this is kind of a picture of what we have so far. So to complete this test bed, we still need to add our actuators and test modules, but that's what we want to do by the end of this summer. And then going forward, we also want to develop out our other test beds for evaluating individual components of the finger, such as tendons, joints, and the bones. So thank you for listening. Please come visit my poster.